Hello, it's Scott Manley here, and today we are looking at Universe Sandbox Squared. Universe Sandbox Squared is, of course, the sequel to Universe Sandbox, not to be confused with Universe Sandbox 2, which was actually the first version of Universe Sandbox appearing on Steam. Which, incidentally, on June 1st should be available for a super cheap price, or rather the cheapest price yet, from a link which I'm going to include in my description thing, in the description section. If you're interested, take a look at that link. Yes, it is an affiliate link, and I will actually get some cash from it. But I promise to make sure I spend it on things like beer and stuff for my live streams. Or, yeah, maybe if I get a lot, I will do other things. I've no idea. I just figured that Universe Sandbox being cheap is worth talking about Universe Sandbox again. So yeah, Planet 9, that's been some big news in the last year or so. Planet 9 is, of course, entirely hypothetical, has not been observed, but the evidence for it is really interesting from a dynamics point of view. So what we actually have here is a simulation. I can run the simulation a bit faster. We're running this at years every second. I can select this and actually do years per second. It says 3 years per second. So everything's kind of moving around here. Now, what we have on one side is Planet 9. On the other side, we have a bunch of Kuiper Belt objects. Now, what's interesting about these Kuiper Belt objects is they all are on highly eccentric orbits. They go way out into deep space. But also, when they were simulated in an integrator that calculated their orbits, it turned out that none of them ever had any interactions with Neptune. They were kind of stuck out in this orbit, and the only massive object in the outer solar system is Neptune. And that's responsible for stirring up the Kuiper Belt in all sorts of interesting ways. But these ones were too far out to be disturbed or controlled by Neptune. And also, over time, if you have these things out in these eccentric orbits, the galactic tides will tend to randomize their positions around the orbit. And yet, they all seem to come out one side of the sun. And also, they're kind of confined to this plane. So a bunch of mathematicians who basically said, you know what, maybe this could work if there was a Planet 9 out here, about 10 times the Earth mass, and this was coming down and periodically, well, you basically constraining these things through resonant action of its own gravity field. This is entirely hypothetical, and there is a project to kind of look along the potential orbit space, which is quite large to be honest, just to see if there is anything large enough and in the correct position to account for this. It would be amazing if they found it. If they didn't, it would be a challenge to explain this whole formation here. I look forward to seeing how this continues. Anyway, let's take a look at some other stuff. Let's actually pay a quick visit to, of course, Pluto, which is another large Edgeworth Kuiper Belt object. Pluto, of course, is in a 3:2 resonance with Neptune, so it's one of these objects that is constrained by Neptune. It's one of the largest. There's another type of Kuiper Belt object called a QB10, which is, QB1 is the prototypical Kuiper Belt object. Anyway, this is New Horizons flying through the system, and you can kind of see what happens here, where the moons are, where they were located. Styx, Nix, Charon, Kerberos and Hydra. And of course, the Pluto texture will no doubt be getting a little bit of an update over time. I can double click on it and take a look. Yeah. Oh, I guess we do have something that... Oh, yeah, there we go. See, on one side we have a nice heart and what do we got? Tomball Planum or Sputnik Planum? I forget all the terminology, and that's really embarrassing. And on the other side, they filled it in with generic craters and things like that, because we didn't really get a view of one side of the planet, largely due to the light never being right or being too far away. Anyway, of course, New Horizons is continuing off back into the outer solar system, or into the outer solar system. It can't stop, it can't come home. And out here, it's looking for potential encounters, and I think this is the one that's most likely to encounter, but I could be wrong. They're going to make a course correction which will bring it right by one of these objects, and we'll get a look at another Kuiper Belt object, which right now is a rather dull and generic shape. Not genetic, generic. Anyway, Universe Sandbox, on top of the climate simulation, the stellar simulation and all that, obviously the gravity simulation is one of the cool things, and one of the ones I do like to show, which is kind of fun because it's chaotic, is the third stage of Apollo 12. Now, Apollo 12, well, basically the Apollo missions, the ones that were going to the moon, they tried to crash their stages into the moon, but Apollo 12 was unable to do that because I believe it used up too much fuel during ullage burns or something like that. I vaguely forget. Anyway, around 2002, someone identified an asteroid orbiting the Earth. It was J0023 or whatever. Anyway, it was identified and they thought, wow, this is a 30-meter object orbiting the Earth. This is really odd. So they figured out that the most likely thing was that it was the third stage of Apollo 12, still orbiting the Earth, because it had never escaped into deep space, or if it had certainly come back. Anything orbiting the Earth in this kind of orbit is going to have to deal with the moon, so the fact that it was orbiting the Earth implied that it was certainly a young object. And being identified as a 30-meter object, well, that made it a lot bigger than what the Apollo 12 upper stage should have been. But, well, guess what? The Apollo 12 upper stage was painted white and therefore was a lot brighter than any other asteroid. So, if you don't know, many asteroids, when we photograph them, the only thing we can do is figure out how bright they are. And from that you have to estimate just how likely they are, or just what their size is. So here we go, this one had an encounter with the moon, and the moon finally kicked it off, and it will continue to orbit around. Notice these cycles here. These are because we're of course viewing everything from the orbit of the Earth. If we switch to the Sun, I believe we can change the trail generation here. Now, how do I do that? There's a viewing option somewhere. View, trails. Trails are here. Show more trails. Lighting, I don't know where it is. The trail option, I believe, is... I can turn them off and then turn them back on, but no. We're following the sun for some strange reason. And man, let's show the orbits. Oh, there we go. See, that's more realistic. Now you can actually get an idea of where everything is. So the third stage of Apollo 12 get kicked out and it is falling away from the Earth, and eventually it may re-encounter the Earth and get captured again. Here's one of these things that's interesting to follow. Perhaps one day it will fall back to Earth and we'll get some awesome salvage, or perhaps by that point we will have wiped all ourselves out and this will be some sort of artifact from the gods. Oh, supernova close up in real time. This is how fast a supernova actually happens. Oh no! Well, this is their simulation of the supernova. You can actually look at it. It's a 9 solar mass object, and this is exploding out. Look at the luminosity here. Oh, actually that's not so realistic. Yeah, so it turns into a sun nova remnant. There we go. Yeah, now this has a VR support for the HTC Vive, and I gotta say, a lot of enjoyment with that. But most of my enjoyment of that tends to come from throwing stuff at the Earth. We have simulations all over the place. There's all your human scale things like that, stress tests, other tests. And actually, if you come back, there are tutorials and lessons. There's science lessons on scenarios and stuff like that. So if you're trying to use them as a teaching aid, it has all that stuff. Create simulations from presets, so you have like random solar systems or things like that. Or you can actually pick some more interesting. Oh, here we go. Choreographed orbits. Now, if you remember, there are weird orbits like these. These are braided orbits. Some of these work better than others. Basically, some are stable and some disintegrate very quickly. But there do exist mathematical solutions which, when simulated precisely, can do very weird things like this. Most of them require all the masses to be identical, and if they're not identical, or if there are slight errors in the calculation, things eventually start to fall apart. Like, I think this one is going to fall apart. We'll find out. This one is getting pulled out of place ever so slightly in each iteration, and that means that it's taking different amounts of time, and as that's happening, yep, we're going to get a collision. Which one's going to collide first? Place your bets. Oh! No. Oh, 3D is confusing me here. Are these ones going to collide? These are obviously full-scale moons here. Oh, wow, the moons are staying alive. What about these two? Nope, they're not doing that. Oh, there we go, finally, into a ball of molten moon material shooting off into the distance because it still has some issue with close encounters. Yeah, I mean, let's be clear, Universe Sandbox doesn't do orbital mechanics perfectly, and it doesn't provide all the tools that you would expect in something that was suitable for academic publications, but at the same time, they have come on in leaps and bounds compared to the original Universe Sandbox, where the Euler method ruled the day. Incidentally, if you're wondering what we're doing, we're dropping the Earth into the Sun. Why? Because I want to see if the Earth picks up a tail like a comet. Instead, it appears, well, I'm trying to see if there's any sea levels getting boiled away or whatever just yet, but I think this is going to take too long to get down to the sun. And, 7 miles of ocean isn't going to evaporate in a few minutes. Yeah, usually you see areas around there that kind of show up as seabed. Or another one that shows up, way down this area you might... Yeah, maybe there's something happening there. But, oh no, here, see next to the UK, that is Doggerland. Doggerland is an ancient area of land which was inhabited. It was inhabited because the Ice Age dropped sea levels, and because the sea levels were so low, this area was exposed, and it was used for hunting. It was very fertile because it was fed minerals and nutrients by the Rhine. So yeah, look, oh! And there, finally, the sun consumes the earth, Doggerland and all, dogs and cats, humans and everything. Yes, we can watch all of these things evaporate into a giant ball of plasma, which barely notices it because it's like a million times heavier. Well, yeah, hundreds of thousands of times heavier, not quite millions. Anyway, yeah, one of the things that you can do in this is climate models, although they're obviously super simple, but they're fun to play with. So yeah, this is obviously for people that really want to, if you want to do like lessons on, CO2 levels, but one of the interesting things I like to show is that if you increase the eccentricity, right, and this is the complicated one, if you increase the eccentricity, so that's 0.1. So this is calculating the temperature here under climate. Now, by changing the eccentricity, what you've done is you've moved the periaps down 10% closer, and you've moved the apoaps out by 10%. And it turns out that while that difference seems very equal, it actually results in a net reduction in the amount of sunlight you get during a year, because when you are closest to the sun, you're moving fastest. When you're furthest from the sun, you're moving slowest. Therefore, the climate will tend to cool down as the eccentricity of the Earth increases. And this has happened, throughout history. This is called these are called Milankovitch cycles. They're well documented, so you can actually see the seasons happening here. And I'm guessing if we watch this come around, we'll see new seasons come out. So there's the Himalayas there. Now I'm wondering if it will actually result in a much cooler system, or if we really let this run for long periods. I'm not sure I can simulate it for that amount of time. But another way to do it, to really cool it down, is just to cut down the amount of greenhouse gases here. If we nuke those, then the temperatures during the winters will really start dropping. Oh. And there's an interesting thing you can do here. You can actually cut down the amount of greenhouse gases way the heck down. And what happens is you'll get the snowball Earth state, right? So snowball Earth is about 600 million years ago. That was when essentially the first bacteria came along that could take carbon dioxide and convert it into sugars. And what happened was they started taking all the carbon dioxide out of the atmosphere. They started putting oxygen in. They, oh yeah, all sorts of crazy stuff happened. But essentially, by removing these from the atmosphere so efficiently, they caused the entire planet to freeze solid. And I think at 50 parts per million of carbon dioxide, we're going to have a serious ice age here. And this is obviously happening way faster because I'm obviously exaggerating things. The thing about ice ages is that as the ice creeps southwards, the albedo of the Earth goes up, right? So you can actually see a graph of this. Over time, the albedo gets higher and higher, and the albedo is how much light it's reflecting. So if the albedo continues to rise, then you start reflecting more and more of your light back into space. The surface cools more and more, and the temperature drops more, so you have more ice. So with more ice, you reflect more, and so on and so forth. And under the right or the wrong circumstances, you can, in fact, freeze the whole Earth, and from that point it's very difficult for life to recover. And that's one of the big questions in paleogeology or whatever. Or it's not paleogeology, I don't know what it is. I think paleogeology is a word I just made up. It's basically looking at the history of the Earth and life on Earth. How did the Earth come back from the great snowball period about 600 million years ago? And the general theory is that this was because when the Earth froze, the precipitation froze, the clouds stopped happening, and therefore there was no precipitation to remove carbon dioxide from the atmosphere. So volcanic gases would build up, and they weren't removed from the atmosphere, and eventually they flipped. It managed to get enough carbon dioxide into the atmosphere and methane, whatever else, everything. And we had a small sea started liquefying, and then, of course, the albedo started dropping, the amount of sun getting collected increased, and the Earth returned to... The Earth basically unfroze very, very rapidly. Look at this. Look, see how this is going nuts. Snowball Earth is a thing, and to get out of it, you need a huge amount of CO2, because at this point the temperature has dropped precipitously. We need to push this way the heck up, and then I don't think we're going to be getting out of this. The only way to save Earth now is by huge quantities of greenhouse gases from those volcanoes. Come on, volcanoes, we know that you want to save the Earth and all the life that lives on it, so you can later burn down their homes with your lava. Just think about it, you need to unfreeze the Earth, otherwise you won't have people, and without people, there will be so much less news coverage of your awesome eruptions. Anyway, yeah, look, seriously, Universe Sandbox Squared, of course, it's still on Steam Early Access. If you watch this on June 1st and you haven't bought it, check out the link and you might be able to get it cheaper than usual. If not, you know, you can always watch videos and ask me about stuff here. And I do not think I am going to be able to get this Earth out of this. I'm just putting in so much greenhouse gases, and the temperature is barely budging because of all that shiny white Earth ice on the surface. Oh well, if we ever unfreeze it, I'll be back. Until then, I'm Scott Manley. Fly safe.